effect. And there was also, I think 2 years ago, people are able to observe this kind of clock differences with more or less regular atomic clocks. So they can almost buy commercially, placing them at the ground of a high tower, at the top of a high tower in Japan. And also could there observe this time dilation. Well, this is the redshift, and the fourth concept I would like to emphasize, because this gets us closer to the experiments we have to do, is the Shapiro effect, which goes back to Shapiro in the early 60s, who sent radio light from Earth to Venus. That's reflected at the surface, at the atmosphere, and comes back. And you're seeing there's a time delay of 200 microseconds, which can be only explained by having this space-time curvature here due to the Earth and the Sun here in the middle. And that was the beginning of this kind of light bending, so to say, due to masses. There was a continuation of other experiments to improve these results. A few years later, there's this famous high-stake antenna in Westford, where they continued more precise experiments with well, about 10% accuracy. And nowadays, people use satellite, which they place in a good position, so to say, that the light or the radio waves go close to Sun, and then you see here with precisions up to 10 to minus 5 results that confirm that are that close to what GR predicts. And that's right now the research this year of the Cassini probe just a few years ago. And I guess Cassini is still flying in the orbit and is still used for investigation. So these are the, as you see, the classical tests that people used, so to say, a classical light or classical physics concepts to probe the effect of GR. Of course, it's interesting to see how quantum physics is interplaying with gravity. And there are a few experiments, and the first is the one I would like to mention. It goes back to neutron interferometry, which was among the first generations that people had access to a single quantum particle. Neutrons are easy to, well, you get them from reactors, but they're slow, so you can easily manipulate them. And there's experiments by Colella, Oberhauser, and Werner, who basically built a Mach-10 interferometry for neutrons. So how does it look like? A neutron comes here, then has the chance to go two paths, either this way to C or this way to B, and then it's recombined here at D, where after this slit, you don't know if this path was taken or the other path was taken. So regular Mach-10 interferometry. The point now is that they were able to tilt this, that C and B have different heights. So they could basically flip this, that C is higher from the Earth than B or vice versa. Basically, it's a rotating wheel. And by that, they were able to introduce a phase, because the neutrons explore a different phase, the Newtonian phase, with respect to the height. You see, this comes in here. And when you now rotate, what you see is you get a phase shift linked to the rotation of the plate on this plot. And here, that's the fingerprint that they got this phase pattern due to the gravitational influence. Okay, you can also explain it as an Aranov-Bohm phase, because it's affecting here really just as a phase on the involvement here. And that was the beginning in 75. The quantum system can explore the interface with gravity. Good. Let's put things together. What has been done and where do we see our need for our experiment? So I make a table where I say, well, this is the gravity concept. There's Newtonian gravity, so a result can be explained by Newtonian theory, and there's experiments which really require the general relativity with curvature of the metric and curvature of space-time to explain the results. So with classical physics, Newtonian gravity was, explored and confirmed, well, since the 17th century. If we look to the things we just went through, then there were the classical tests of GR, okay, with clocks. So basically, these are for me like classical devices, just things that measure clock, even though you use atoms. It doesn't require actually quantum mechanical principles besides maybe some details, but it's more or less a classical thing for me a tool that explores general relativity. With quantum mechanics, I always implicitly think of the particular features that quantum mechanics provide, which cannot be found in classical physics. That's the superposition principle, quantum entanglement, and so on. And I really think about those features which are interesting to face with gravity. And that was done, as I showed just before, with neutrons. So they use really single particles, superposition from neutrons, and they've seen this phase. But the phase here, and that's the important point, can be also explained by Newtonian gravity. So it's not really needed, or actually cannot basically explained, or it's needed to have this general relativity concept here because of just having a phase. And that's true also for follow-up experiments based on cold atoms and even Bose-Einstein condensate. All those observe phases due to gravity, and therefore a fingerprint of this Newtonian gravity, but not a true GR effect. So in essence, the problem that we have seen here is that all of the beautiful experiments done so far, okay, do not provide unique signature of GR and quantum mechanics in a single experiment, okay? Because of this reason that those experiments could be explained by Newtonian gravity. So, and that was the birth or the reason for saying, okay, what about of photonic quantum systems, because photons are intrinsically massless, okay? There's no way to use this to explain this by Newtonian gravity. By having massless particles, you automatically link to GR in space-time, and that's the reason why we are dedicated to do experiments with photons and seeing influence there. What's the downside? Well, photons have no mass. That's good and bad. Bad because it means you have a way stronger interactions or effects of GR, which makes the experiment much harder to build and to basically observe the effects from general relativity. But let us get there by seeing how the experiment works. Okay, so in essence, we have to build a photonic interferometer, which can be seen as the Shapiro version in the quantum regime. So let me put the pieces together, how we build those things. So of course you want to see the difference of gravity of GR, which is linked to height when you use Earth as reference system, and we work with light. So let's consider the following case: you have a laser, you send laser light to a receiver, and then of course we know there's a particular frequency given by the laser or the atoms and so on. And that's here. You can also link this to a clock that this person has, and he measures the frequency coming from the laser. Well, that's in this reference frame. If you have another reference frame and put the guy here up in a height, let's say a few floors up, then this can do the same. You have a laser that sends a laser light. This guy takes a clock and measures the same frequency if he was basically there in his own reference frame. However, if you're being an external observer and you compare those two scenarios, that you have one here at the ground and one here in the upper level, so separated by some distance height, then you would observe the redshift that this upper guy observes due to having either different clock in his hands, or if you would prefer this explanation, by having here this redshifted laser light up there. And that's precisely what I'd like to use for our experiment. We have in mind to take, instead of lasers, quantum light, single photons. We take basically two paths. One is here on the ground level, other path here in the higher level. And when you now take a beam splitter where there's a 50% chance that the light is going this up here, this path, so that's a mirror, or this path, okay? And then you recombine, and then you measure the light coming out this detector, that detector. Then you will see that there's a phase shift because this light up here observes this redshift. And you see the wave packages that come out, they're not overlapping anymore. You see that there's different phase shift. And the phase shift is really dependent on the height. So when you get closer, then we see also the phase shift here is smaller, and therefore that's the link to the gravitational influence. And that's the thing you can measure at the end, even though it's a tiny effect, but in principle you can measure. So what do you do in reality? Well, you build something like this, that you have now here beam splitters, mirror beam splitters, and then you will see at the end that you measure different clicks at this detector or that detector. You see here, this detector will go up. We get more clicks when you increase the height, so it's when you go higher. So due to the phase shift, we get more clicks here. And of course, the clicks that you have more here are reduced by the complementarity amount on that detector. That's the essence of the experiment we have in mind to do. Good. Well, the theory of that goes back to actually just a Buchner's group who looked at clocks at different heights and how they interfere. This was then turned into something we can do. So we turned this into our clocks as photons and redshift. And we did investigation with a few experts. We are super happy about having this collaboration in particular Piotr and Nergis Mavalvala from the MIT LIGO group, so LIGO at MIT, who helped us to make a proper calculation and investigation, at least from the theory. Does it work? Can we do it? And do the numbers fit together that this is worth to do an experiment? And the short answer is yes. And I can show you now what is the result. So the thing that we have in mind is, again, this interferometer. And the question is, what actually the parameters that we need to observe a phase shift? Okay, and the phase shift here is given in essence by the length, okay, of the interferometer times the height. In other words, the area counts for making the phase shift possible. So you see that's good. They have length and height here up there, but the problem is it's divided by c cubed. So in essence, the phase shift is tiny. Okay, this makes it challenging. We need a big interferometer, and big is always hard because big requires it's hard in terms of stability and also in photon loss, because single photons are hard to get in a controlled manner, and you would like to keep them. You want to have them as long as possible here, traveling, and then you can observe many of those at the detectors. Good. So that's the phase shift, which is linked to height and length. If I put the numbers here in more quantitatively, we also have beautiful work with follow-up paper here with Piotr's group and Beck about properties of light in the fiber, because it comes up in a second. We have to use fibers for achieving these long distances. And why? Well, before I come there, let's see the numbers. So it turns out that the gravitational interaction changes the wave vector by this small number, 10 to the minus 9 per 1 meter height. Okay, let's say if you just go 1 meter in height, which is a thing we can do in the lab, that's say a height difference if we're comfortable to stabilize things, then we have now to increase the length. And if you put this number here, 100 kilometers, which is the longest length we can do with optical fibers. If you go more than that to bigger lengths, then the losses are so big that at the end no light comes out. So if you take 100-kilometer fibers here and there, then it turns out that the phase shift you will observe due to gravity is 10 to the minus 4 radians. Okay, well, that's small. Okay, but it's not crazy. That's something that people normally can read out. If they have strong lasers and these phase shifts, they can read with no problem. The thing that's new here is, well, you have to stabilize a very big interferometer. So in essence, you have basically a sensitivity of the difference in length, okay, is 10 to the minus 16 over this entire interferometer. Okay, it's called strain sensitivity. So just to put this in respect, LIGO is 10 to the minus 21 or 10 to the minus 20. Okay, so we are not LIGO, of course, but we are not that far away what big LIGO achieves. Okay, so in our eyes, that's really the maximum you can probably achieve in the laboratory as a tabletop experiment, and having this kind of tiny difference in length you would like to read out over this beast is of course challenging in terms of stability, and I'll come to that in a second. Good, and as I said, we cannot have more than 100-kilometer fibers because here the transmission is already just 1% per single photon. So here the numbers summarize that's the phase shift for this formula. We have this height of 1 meter, the length of 100 kilometers, and we expect this 10 to the minus 4 radian phase shift. However, for reading out such a phase shift, you want to be, that's the rule of thumb, 1 order of magnitude more precise. So we need actually this resolution, which corresponds to being able to see a tiny frequency shift of 10 to the minus 17, also delta F over F in this regime, which is very hard for lasers. And I'll come to it in a second. So the take-home message is, it's not easy, but we still think it's possible and worth to do. So that's a schematic drawing of our setup. So we come to that in a second and later. We have actually not one arm, but two, also three arms, not 2 arms, but 3 arms, because we have to reference different heights, and we had in mind how we can basically get some kind of tuning in there, because you would like to read the signal not as a constant factor, but something that you can tune to be sure, yes, that's your signal, not a noise contribution. And on the right side here, you see all the things that we investigated, what kind of noise comes up. There's fiber noise, there's systematic errors, there's even seismic noise, acoustic noise, and all those things were investigated. We learned a lot. So I must admit, I underestimated by orders of magnitude the complexity of this experiment. And therefore, I'm so proud that we have this excellent team in Vienna that really digged in, figured out what can be done, many trips to MIT guys to help us in reading out noisy signal, because they're really the world experts in telling you, if you know your noise, then you can handle it, and then you can read out the signal, and we know now which frequencies we have to use. We know now what kind of decoupling is needed, and also with the help of Piotr, we could prove that there's no fundamental issue coming up from Sagnac effects and earth rotations that spoil us too much. So we know those now, so now we can really design the experiment to separate the noise from the signal. And you see that many things have to be considered. I leave it here because I rather focus on the scientific vision that we have when of the experiment. Good. So if I have to summarize, the experiment would not be possible without those world experts we are so privileged to work with. As I mentioned, Nergis Group and MIT, PTB, I will come to the second, is responsible for giving us the world's best laser signal. Best in the sense, the smallest noise, okay, the highest frequency, resolution. This is something which really makes our story so nice here in Vienna. And without Piotr, we would be basically certainly lost in understanding GR and all the effects that would come there. And we're very, very happy that Piotr is guiding us and working with us for already a couple of years in this interesting journey. So what do we have? So how does the experience look like? So we have now, see, that's not 2 arms, we have 3 arms. As I mentioned, we would like to switch between different heights so we get the modulation of the signal, because here's a stronger redshift than there, and then we can really read out that. So we learned this from MIT. If you have noise, you have to modulate your signal that basically that you can read out the frequency of the signal all of a noise floor. That's one thing. And to stabilize our this 10 to minus 16 strain the arms, we take now the best lasers we can have. So we have the best lasers commercially viable in Vienna, and we can boost it by a factor of 100 if we connect it to a laser coming from PTB in Germany. So that's so PTB is the Berlin, Braunschweig. So it's the NIST of Germany, okay? Metrologieanstalt, Deutsche Metrologieanstalt, who has the atomic clocks as reference in Germany. And they have atomic clocks which are cooled and cryogenic, they're more precise, and we can get such a signal to make our laser better. Why? Because you have to stabilize these arms very precisely by having additional interferometers, and they're not shown, for each arm to basically compensate every fluctuation that they're stable and can read out really just the GR signal in our setup. So that's the schematic drawing. So we built something here on a very stable platform designed by MIT. Here the fiber coils at different heights, which you can switch between those. Each fiber coil actually has its own virtual clock. Okay, so we have very precise lasers stabilizing these arms. Here's our laser here, and actually that's an interesting side story. So this experiment probably supports the clock dissemination in Europe, because PTB has clocks in Braunschweig, that's by Hanover. They have fibers in Germany to send this across, even to France, to compare clocks, you know, for geodesics and other interesting experiments. And there's currently a fiber going to Munich. And we got money. So Piotr didn't mention, we got money from different sources now for getting the extension from Munich to Vienna, that we can connect ourselves to a laser signal coming from Hanover. And with that, we can synchronize our lasers here in the way that the resolution is boosted by a factor of 100. Okay, we're not sure we need it. Best case, we don't need it. Worst case, we need it. But if we need it, we have access to. And now our experiment somehow helps that PTB sends signals to Vienna. And now, as the rumors were spread around that this is happening, other groups came to us and said, hey, we would also like to have this access, because we work also with atom clocks, TU Wien and so on. And now we shaped a little bit the clock dissemination in Austria, which is a nice side effect. Good, that's the schematic of the experiment. Back to our expertise. So the thing works with quantum light. So that's really our signatures for 10 years. And just make it briefly, what's our bread and butter in the quantum group. Well, we normally take nonlinear crystals where lasers shine on these nonlinear crystals, where there's a high harmonics, a second order effect, which turns into that the blue laser light is turned into 2 red. So 1 blue laser photon becomes 2 red photons. And if you do it in a smart way, you can really generate a polarization entangled state. That's something we generate here. Nowadays, it's more trendy to have actually artificial atoms. So the problem here is it's probabilistic. You never know when the photon is coming. So people thought, is there a better way to get a system where you push a button, always the photon comes out? And that's not yet possible, but in principle, it could be done by these artificial atoms where you build so-called quantum dots. You build semiconductor structures. You confine it in 3D that they behave like as a single atom. When you shine laser there, then basically you excite and you get a photon out, and it comes out coupled in a cavity, so it's efficient. And we have these quantum dot sources which are way brighter, let's say order of magnitude brighter than these sources, and we have in mind to use also those for the experiment because we need every photon for statistical reasons. What's the challenge? Well, that's a technical detail, but the best wavelength for fibers, and best wavelength means where the losses are minimal, is the so-called telecommunication wavelength that's nowadays used everywhere for whatever, phone calls and so on. But it's at this wavelength, it's 1.5 nanometers. And that's an unlucky wavelength because detectors are not very efficient there that we use in regular life. So regular detectors are based on silicon or silicon photonics, and they're very inefficient, just a few percent. That's fine for telecommunication business because they have so bright lasers, they don't care to throw away 90% of the detectors. But for us single photon guys, that was a killer reason for many years to work at this wavelength. But the problem was solved by superconducting technology, which is now on the market for 10 years. And we work with that and even update or upgrade those systems for our needs. And by using so the superconducting material, you have almost 95% efficiency. How does it work? Very simple. You cool down a superconductor to be superconducting. Then you measure the resistance, which is 0 because it's a superconductor. When a photon comes, so you basically have here the superconducting wire. It's here. When a photon comes, it makes a hotspot. Okay, it gets absorbed. And the hotspot means that the flux basically is squeezed to the side. It cannot go through the hotspot here. And if you increase the flux, at some point superconductivity breaks down. Okay, that's happening here. And if this breaks down, then you see suddenly resistance. So, and then when you see the resistance, you know photon was measured there. And you keep the material very small, so it's nanomaterials, for the reason that if it's small, it's cooled down again rapidly. So after a few nanoseconds, the heat is gone, and you see it becomes again superconducting and reaches again this point where it's ready to see the next photon. And that's what we operate. What does it need? Well, it needs a cryostat of the order of 1 Kelvin. So you see here an open cryostat, fibers come in, and it would go down many levels to this 1 Kelvin region, where inside the detectors are sitting. Let's see the detector inside. Okay, the fiber comes, and we read out our signal here with these detectors. And now, as you see, well, these are technical details. You can even resolve if 1 or 2 photons are coming, because at the area where the fiber comes, okay, you can put now several detectors that are like put together like these meanders, okay? And this means when 2 photons come, there's a chance that 2 different detectors will see it. 1 photon goes, for example, to the green detector, another photon to the red detector, and then we get 2 different clicks, and we can tell you, yes, 2 photons arrived here. And for these 4-element systems that we have, the overall efficiency is, you see, 22% is for each detector, this times 4. So really in the good 90% regime for our detectors at this wavelength, our system. That's the message is here. We are happy and glad that we have the technology and capabilities to work efficient with photons as it's required for this experiment. So I talked about single photon and how gravity is influencing our quantum light. But of course, we want to have a real signature of a quantum feature, because single photon superposition is at the end the same that would you observe by laser light in there. So it requires more arguments why the single photon is different, why the single photon detection you have to treat differently as a regular laser light, even though I think it is different, but it's of course nicer to have a stronger signature of quantum mechanics. And what could be better than to use entanglement or really entangled photon pairs? So how do we get there? Well, we can do it, and we use a particular feature of light, which is again something that we use at the daily business. And it's really linked to the bosonic nature of light. How come? So if you have now a beam splitter where you have 50% chance that light, say 1 photon comes here, that light is transmitted, or 50% chance to be light is reflected, then the following happens if you have now 1 photon from this side and 1 photon from that side. So when they come and these wave packages overlap, so you have to describe them by quantum mechanics, then these photons interfere. And the interference leads to the fact that both terms are transmitted, that this one, and the terms both are reflected, okay, that would correspond to that term. So transmission, transmission, reflection, reflection, turns into zero, okay? They, by interference, are gone. And there's a few ways to explain this, but if you be a quantum optics person or quantum mechanics guy, you would say, well, that's the bosonic nature. Photons like to bunch, they're bosons, there's no way to be separated, and they go only as 2 photons there and 2 photons there. One way to explain. Other way to explain is, if you're an optics guy, you would say, well, we know from each reflection here, you get an imaginary I phase shift. And also from this side. So each photon gets an I phase shift if it's reflected. So you see the reflection 1, reflection 2 gives you each time this I times I squared is -1. So you would understand from optics also, well, this term must cancel because of this reflection part here. And that's the case. How do we observe it? How do we measure? So what we do is we look at the coincidences. That means we look at the case where a photon comes out here and there. We look at these clicks from both detectors simultaneously. And that's drawn on this axis, coincidence measurements. And now we tune the delay of a single photon here. So if the photons arrive at different times, then there's no interference. And you will see at this case, let's say here, there's the big difference in delay. You will see coincidences because there's no interference. And photons can go as they wish. But as soon as you change the delay that the photons start to overlap, then you see, so you change the delay that's here on this axis. Then you see that at some point, as soon as the photon starts to overlap, the counts go down. So the coincidences vanishes. And the best point is here, when there's a perfect overlap of photons, then you see there's no coincidence measured because all photons interfere in such a way that they bunch into this state of 2 photons left or 2 photons right in a coherent or in an entangled state. Okay, and that's basically what we do. We tune our delays of light of single photons, and we always observe such a missing coincidence, which is the signature, yes, photons interfere there and can work with it. Good. Why do I bring this up? Why do I teach you about photons bunching at the beam splitter? Well, that's our entangled state. And even better than that, it allows also an increased sensitivity. How come? So if you look at the beam splitter and the photons interfere, that 2 go up here and 2 go up there, then you have an entangled state. So they are really in this non-factorizable state where 2 photons and superposition of, let's say, if n is equal to 2, that's the state, 2 photons up and nothing down, or vice versa. So this corresponds to a path entangled state, okay? And the nice feature why this is interesting for many years in optics is that it increases sensitivity as well. So what do I mean by that? So imagine you have this Mach 10 and you shift now this little beam splitter. So with homeschooling, take it. So when you're not, say, forget about gravity. Let's say gravity is gone, and for a second we just tune this, shift this mirror. Then you change the path length of this arm. And in essence, what you do is you will see at the end that you have interference because we're changing this path length. But now when you write down the state in this entangled way, that basically the photon number entanglement, let's say 1 photon up and down or superposition of n photons or 3 photons, then you will see that the oscillations here increase with the number of photons, okay? Because each photon contributes to a phase here. Each photon carries a phase. So if there's 1 photon, it's EI phi, 2 photons, E2 phi, and so on. And that's basically the way to increase sensitivity, because now you need to move not that far to get already like a λ/2 resolution. So let me show you a picture to that to explain what I mean with that. If you just send 1 photon, which goes into position, then you'll observe with the lambda wavelength of this photon state, the interference pattern. And you know, for resolving a distance of light, you have to go from top to bottom. You need λ/2 as the resolution, it's basically the limit that you have. There's other limit and others, but in principle, that's the rule of thumb. Well, if you have now access to an entangled 2 photon state in this kind of manner, you gain this factor of 2 in phase, and you see the oscillations are twice as fast. That means you just need to go half the way to get top to bottom resolution, and therefore you have enhancement effect of 2 in the resolution and so on. So actually what you have here is a light that allows to go to the Heisenberg limit of resolution, which is nice. So what do I want to tell here? Well, if you have quantum entanglement, you benefit by having better resolutions. And that's the thing you can use also for as a signature for our gravity experiment. And this is called this kind of classes of light, where you make this path entanglement. It's called noon states because you write it like N00N, and people develop this kind of catchy name for this kind of experiment. Good, and that's precisely what we have in mind to do. So we basically have in mind to send also 2 photons. We put them in perfect overlap, and then we hopefully see this enhanced resolution at the end, which is a signature for our experiment that we have also quantum light being affected by gravity. Good. As a run out of time, I would like to show our current status of research. As I brought it up, it's very hard to build such an experiment, and it makes sense, of course, to start with a little lower level of sensitivity as the first preliminary research. So where are we right now? So thanks to Piotr and his team and Thomas, it was shown that the Earth rotation actually introduces a Sagnac effect. Okay, I come to this in a second, what it is. And it's bigger. It's big, quite bigger than the gravity. Okay, that's bad. But the good thing is, Sagnac effect is a geometric story. So by playing with geometry of the arrangement of your setup with respect to the Earth axis, okay, you can either make it stronger or weaker, or even put it almost to 0. So in principle, we know how to handle Earth rotation if we can place our setup in a good angle. But being aware that this effect exists and having in mind we anyways want to work with the Earth and the mass, why don't we use this for the first experiment? And indeed, we want to use the Earth rotation for testing our sensitivity, and that takes us to the thing that's right now built up in our lab. So Earth rotation is based on a Sagnac interferometry, which is in the field of this optical gyroscope. Okay, so rotation or observation of rotation, which is an active field by many groups for seeing tiny fluctuations of the Earth rotation due to tidal effects and so on. But how does it work? So I give you hopefully a brief introduction that's not too still allowing you to grasp the basic idea. So the Sagnac effect says when you send light, okay, here it's a beam splitter, you send half of the light this way, there's the red arrows, and other half of the light, the blue arrows this way, okay? Then you can adjust the path that they interfere, and all the light, for example, comes out, let's say here at this detector. Now, when you start rotating this light, then you effectively change the wavelength of with the rotation and counterclockwise of the rotation of light, okay? And by that, by rotating the arm, you see a different phase shift, and you can observe a different intensity with respect to the rotations here. And that's called this passive sensing that you hear introduced by this rotation. Nowadays, people do something more complicated because it's at the end more sensitive than just looking at detection here. They put non-linear materials using a laser systems in there, which observe these rotations by changing the laser light coming out there, and then look at detectors also at the end, which are influenced by detection here of these basically active materials in there. What's impressive about those things? Well, this is called this ring laser gyroscope, where they send laser light clockwise and counterclockwise with respect to the rotation, and they're super sensitive. So it's impressive just to mention this. They build lasers, this kind of ring lasers of big sizes. So the area counts. The bigger the area, the bigger the Sagnac influence. So the small ones have 1 square meters, but the bigger ones have almost 1,000 square meters. Okay, with big perimeters. And what last thing that you see is they are able to observe deviations of 10 to minus 7 up to 10 to minus 8 with respect to the Earth rotation. So this omega is the Earth rotation, and they see these tiny deviations of the Earth rotation. And this allows to observe tidal effects, and hopefully in the future, that's what people claim, even frame dragging or this land steering effect. Okay, that's don't want to go into that because I would like to learn more by myself how they do it. But it's amazing that this kind of sensitivity can be achieved with such lasers and so on. But it's not really what I want to do. I want to just prepare the stage for our experiment, which is we go to fibers because we have to work with fibers anyways. Fibers are neat because they have a quite good stability over long terms to measure here our Earth rotation with a fiber gyroscope. How do we do it? And now I just show pictures without equations. We do the following. We take a laser source. We send 2 photons here. They come over here. And then what we do is that there's like that's basically, so these photons are in this particular orthogonal polarization state, horizontally and vertically polarized. If you want spin up, spin down, there's a Stern-Gerlach explanation. And we project them in a different basis, so we rotate them in terms of optics, which allows to get this kind of state. Two photons must be either H or two photons either V polarized. And this gives us also a path entangled state if we have a splitter that splits the polarization. Okay, so if the H polar, and it does it, so it means that the H polarized light goes this arm, and the V polarized light goes that arm. Okay, and they go through these coils. There's one coil of 1 kilometer, second coil of fibers of 1 kilometer, and they go through this big 2 kilometer loop. So the H component this way and the V component the other way. Technical details we also correct for birefringence. We take the fiber course at particular angles. These are just details that we are important for optics that this works. So the point now is, according to the Earth rotation, if you place it properly, to basically see the maximum effect of the Earth rotation at 47 degrees, then you will see a tiny phase shift here due to the Sagnac effect. And since you have a two-photon state, it's even enhanced by this factor of 2 here. Okay, so a Sagnac effect is the phase and enhanced by factor of 2 because of this path entangled photon state. And when the light comes back, then we catch it here and we project it to those different terms. This is details about optics. But the point is the amplitudes of this term, or this polarization term, or this polarization term, you see both H, both V, or orthogonally polarized, is basically linked, okay, to the phase that we catch here. Okay, so by looking at the end, what's the amplitude of this term, or this or that term, gives us the signature about the phase we got from the Sagnac effect. And that's what we do at the end. We split the light and we measure HV component. We measure both photons here, 2 H components, this one, or we measure here at the end 2 V components according to, well, basically this kind of phase that we get up from the Sagnac. And what do we get at the end? So this is just the cosmetics. What we get, we expect for our Earth rotation a 3 milliradian phase shift, which turns into a slightly imbalance of those terms, which is seen as 25.15% probability to get these two terms and 49.7% of this term, which is different to having perfect zero phase if there's no Sagnac effect, but this is equally balanced. This is 50% and this is 50%. So we see this deviation as our basically as our signature. So as I mentioned before, we would like to see signal by having something tunable, okay? Because a constant signal is always a pain, because they were never sure if this is statistical error or constant error. So how can we tune it? How can we switch on and off the Sagnac effect, so to say? And we do it by placing here an optical switch. That's the reason we have two coils, and the switch basically makes this. It twists the connection of fibers in a nutshell. That means in one configuration, they are opposite polarized. That means the light goes, so it goes like one direction and then the other direction here, the light. So the Sagnac effect is compensated because half the way it is left spinning and the other half the way it is right spinning the light. So it goes back to zero. Or we change the switch that they add. So it's left spinning and again left spinning. Okay. So by that you have two coils which are like either like this or like this connected. And that's the idea of our very good optical switch here. And by that we can switch to no Sagnac effect to Sagnac effect. And this allows us to observe those things. And that's happening in the lab. So how does it look like? That's the lab. It's here. These are the two coils. So we see it better on this side. This is the one coil. This is the other coil with 1 kilometer length. The switch is not shown here. It's actually at the end. It's a small thing in the frame, and it's oriented in a, how to say in English, cadencia, of the gimbal mount, where you can change the angles of the entire Sagnac interferometer in such a way that you have the biggest effect with respect to the Earth rotation. But as you know, the Earth is rotating, and we have our latitude is 47th degree, so you have to of course correct by that to have the maximum Sagnac effect. And that's the reason we have this arrangement here for our setup. And that's the first step of doing a precise measurement, which is soon followed by a big interferometer for observing gravitational effects in single photon. Good. With that, I hope I could shine your light into our plans and vision. In essence, the summary is here. So we have now a precise interferometer where for the first time, okay, quantum light will be used to observe the Earth rotation. So we started continuous laser light. That's nothing special, but it's more like alignment purposes. And so we want to switch to these 2-photon noon states, as shown before, to really use quantum mechanical enhancement. So it's called quantum enhanced sensitivity or quantum metrology in our community, to see the Earth rotation by noon states. And based on the insights here, we build the next generation of interferometer, which is really has the plan to see the gravitation effects on quantum light on single and entangled photons. And we believe it's important to do so, this experiment, because the fact that if these massless systems, okay, really massless particles, means that there's no way to explain our results by Newtonian gravity, and therefore we really go beyond Newtonian descriptions. And it says, well, it's really a unique fingerprint that we have a GR effect measured on quantum light, and that's the vision of this. Good. With that, I want to thank so much the team that really is from day one, and it's already a couple of years, 5-6 years ago, supporting this research project. There's Christopher Hilweg, Bob Peters, and Raffaele Silvestri working on the experimental side and in my group. But we're very privileged and happy to have Piotr and Thomas. I couldn't find a picture of Thomas. I tried to steal one on the internet, but I couldn't find the proper one. So it seems to be an eyewitness program that Thomas is currently protected. I want to thank Thomas and Piotr so much for being open to support our, at that time, crazy idea, maybe, this research direction. And without the help of Piotr and Thomas, we wouldn't be there yet with all these insights, understanding. And they never get tired when we ask simple questions in their eyes about gravity, and they are so helpful for us to make this experiment happening. And I'm really happy for our collaboration, which happens within tourists, but we wouldn't be there without the serious support of our friends. Good. With that, thank you for your attention, and I stop here, and it seems to still have some minutes left for questions.
Okay, thank you very much, Philip, for this excellent, clear talk and interesting talk. The floor is open for questions. I try to see who wants to raise his hand. So before you think about the question, let me ask you a question.
Kann ich kurz einen Kommentar? Ich glaube, ich habe meine Hand gehoben.
Ah, yeah, now I see it. Yeah, okay, Herbert, go ahead.
Only a short commentary. You were talking about the cow experiment. Yes. And since I'm from the Technical University, I want to bring in the name of Helmut Rauch, yes, who was, so to say, involved in these neutron interferometry experiments, mostly with the 720 degrees rotation. And you pointed out that the cow experiment is actually explained in Newtonian gravity. And Helmut, in his, unfortunately, he's passed away last year. And so, I mean, in his late book, he has also an explanation using, so to say, Eigenzeit description within the Schwarzschild geometry. So in that sense, it has a little bit of flavor of general relativity. This was just a comment for the first experiment you were talking about in the quantum regime.
Yes. So notice comments from Helmut Rauch. Thank you for pointing this out. Of course, neutron interferometry would not be there without Helmut Rauch. He was really a certain pioneer. You know, he influenced people.
Yeah, we are very sad that he passed away, but
absolutely, yeah,
certainly very influential.
Yes, of course. But to come back to light, with light, it's clear that there's really no mass, and you can avoid any additional arguments that Newtonian gravity plays a game there. So that was for us the vision to do something with.
No, it's more or less, I mean, the equivalence principle that you would expect. I mean, if you do it either in curved spacetime or you do it in Newtonian gravity with acceleration, so if this fits together, then it's fine, but should be corrections.
I have a question.
Go ahead.
May I ask a question?
Yes.
Okay. So the question is related to the middle of your talk, where you have shown us a laser beam, let's say upper and lower. Yes, there were two
Yes.
laser beams, and you measured something, which the phase shift, which depends on the difference of the levels of those
Yes.
two beams. Yes, but and this was a redshift, let's say. And my question is very general. Can you inverse the experiment? Can you pass from red to blue shift, or inverse in time, or whatever? So that the phase shift will be opposite, and then you come on the same let's say experiment, but roughly the laser is up and the detector is down. You know.
Okay.
You understand my question?
Let me rephrase it if I understand. So you're saying, can we have the opposite, that we get the blue shift by putting detectors down, and you? But
yeah, I can say that the length which is in this phase shift is negative. You know, this age becomes not positive but negative.
It boils down to rotating the machine.
Yes, but isn't it the same? Because you can, as soon as you have a difference in height, you can basically, depending on where you're standing, you can talk about red or blue shifts. No, I think so. The answer is yes, but at the end, the bottom line is we want to see a red shift that can be only explained by GR. No, so, and I think the answer is yes. So for me, what you were saying is, it's really a question about your reference system, where you put yourself. Do you put on the lower level and you see something blue shifted, or is that from the ground is something red shifted? So the answer is yes. But it's
But
equivalent
can you
in my
do the
eyes.
experiment parallelly? You know, just two different experiments in some sense. Then this, can you see some symmetry with this delta phi?
So in some essence we will do that. Okay, so because the build is, we have three levels. There's one height, height 1, height 2, height 3. Okay, so in that essence we will play with different heights and switches, because we need a modulation. We need a signal that says a stronger gravity. We need different gravity influences or different redshifts that we can read out at the end as an oscillation, because that's our signal. So we have to play with this concept, because we learned from experts, there was LIGO, that a constant signal is always hard to read out. If the signal is always there, then it's very hard to separate from everything else. You need a modulation. And this probably brings it back to your suggestions. Yes, we have different heights. Okay, let's say small red, big red shift, or if you put yourself in the middle, one is red, other one is blue shifted. We have this, and we see the modulation between those. And that's precisely what we build with the help of LIGO, because it's not simple at all to build a device so we can modulate that. And this, I think, brings it back to what you suggest. We see both influences, so the different relative different influences of gravity. So the answer is yes.
Yeah, thanks.
Okay, further comment? If not, I may ask a question concerning systematic errors. How important is it that the velocity of light in that fiber is constant, or is equal? I should say equal, or this is.
So thanks to Piotr, I was taking a closer look on the propagation of light in fibers. So thanks to Thomas. Okay, so your question about the speed of light, as long as it's constant, okay, and nothing is changing over time, it's fine. So at the end, we have one fiber up, one fiber down, and then there can be even a different length or so. Or there can be even different in some aspects. As long as it doesn't change over time, it doesn't matter. So you build a device, then you tune it, that you see the interference as you expect, and then comes the challenge. You switch on magically the switch who says don't move. Okay, and don't move means from now on they have to consider all the noises that might come up. There is so a nice story I like to tell. When people investigated about fibers from the practical aspect, we said, look, who are the fiber experts to ask? Okay, we went to LIGO. They will learn LIGO worked with Revise, said in the beginning he worked with fibers, but he's not too sure about all the properties and so on. And after asking 3 people, were pointed to the US Navy. There's a Navy Research Center, and they're the world experts in fiber. We went to Washington, D.C., and we learned that a small fraction they can tell us, which is even amazingly knowledge, and a big fraction they cannot tell us. Why? Because fibers are used at submarines for being surrounded, the submarine fibers. And if there's a sound wave, something like this coming, they give a phase shift from the fiber, and they can read out precisely which direction in the sound wave from another propeller comes. Okay, so I like this story to tell that actually the Navy it was super helpful in us for building this interferometer. But back to your question, as long as we know as long as it's stable and we know what's happening in the fiber, there's no problems with speed of light. Okay.
Thank you.
Okay.
Is there any further?
Yeah, so I have a question.
Yes.
Yeah, so we've been interested in various things related to polarization, and we're trying to do some toy calculations concerning propagation of polarization, essentially around an optical fiber in a gravitational field. And so I'm curious if what's your expectation? Is it conceivable to have a stable sort of actually experimental setup of the type you're considering, where you would be able to observe effects related to polarization of the light?
Very good question. The polarization is a big issue. Okay. So in a dream world, you would like to keep polarization fixed. We don't need to consider that. Okay. One way to do it, you would take polarization maintaining fibers, which are built, as you know, that this doesn't work because they're too lossy. Besides being too expensive, would be millions that we have to spend. So we have to work with regular fibers. The polarization is rotated. Okay. So we learned also here from LIGO and the Navy guys that you can stabilize fibers as long as ours in such a way that the polarization is of course changing, but it comes with a given input state. Polarization comes in and the polarization comes out a certain degree. We can keep it stable in such a way that there's that basically this will not affect us too much. So we can freeze everything to a degree that the polarization is not drifting in the fiber. Okay, and that's the challenge that we that's what we investigated for last year in stabilization techniques, that the polarization drift is basically non-existing or very small in the fibers. So we learned how to do that actually.
Oh, that's very interesting, because I mean potentially there's a sort of geometric optics effect on the polarization vector in a gravitational field.
Yes. So you're saying so this I would like to pass on to Piotr, because they did calculations on polarization, and I think, if I remember correctly, it shouldn't affect in the fiber. So you're saying, is gravity affecting polarization in the fiber? This is what you're saying?
Yeah, because I mean there are similar calculations have been done for massive spinning particles, and I think, but I mean this has not been done to the end. I mean, we should discuss this with Piotr eventually, that you can have a similar effect on photons in a fiber sitting in the gravitational field. But this needs to be investigated. I mean, this has not been, we have not finished this, but it would be curious if one could potentially see such effects on the polarization of photons.
Can you hear me? Because I had problems with the microphone.
Yeah, yes. So, would you like to comment? Yes.
Yeah, so just a quick comment. In the paper we wrote with Bobby and Christopher and Philip, we work out the electric and magnetic field after it went through the fiber. So we have a formula for that. My memory is that our preliminary thinking about it, that we will not be able to measure that, but maybe it's a good point in time to just take this formula we worked out and revisit them. That's one comment. And the second comment is, well, a question to Philip. So how far are you now with the rotation experiment? Do you have numbers now? Is this still in a debugging phase? Or?
No. So the measure right now with laser light. So the numbers are boring to show because this is just like characterizations about. So
no, but I mean experimental results, right? So
yes, we have experimental. So we have experimental curves, which I did not show you, because it takes 1 more month to have something useful. So right now we measure with continuous laser light, and they optimize in coupling and so on. But the plan is that by end of March, everything is measured with single and with quantum light. So the source is prepared, it's ready to shoot, and we have an internal bet in the group that by end of March, okay, so after spring break, everything is measured. So I hope that it looks good. So I would say in a couple of weeks we have the data.
Great. So I'm looking forward to meeting you and seeing.
Yes, absolutely, should catch up. Yeah, sure.
Thank you. Just to finish, I want to bring up a question we have discussed with you, Philip, namely the question, what is really tested? Is it, I mean, is it what has been mentioned, the so-called equivalence principle? Now, the equivalence principle is also valid in Newtonian theory, and it's valid in any metric theory of gravity. So you emphasized several times that this goes beyond Newton's theory. And I think we had a debate on this, and I'm not sure, because after all, one knows that light is, even Einstein, before he put forward his theory, knew that light is influenced by gravity.
Yes,
so,
but here I'm happy to answer in the words that I learned from Piotr, that if you use just the equivalence principle, you offer a factor of 2. Okay, so you have to consider also the change in the metric, so you don't get the right number. Okay, so the thing that we test here is we would like to explain. Our explainer allows to exclude, as Piotr pointed out, some post-Newtonian concepts. If you just use the equivalence principle, then you would be wrong by factor of 2. And here we think it's a true signature experiment that you must use GR and quantum mechanics, in particular for the 2-photon state, to explain the results. So the purpose is you want to have one experiment where you need both theories truly, GR and quantum mechanics, to explain the results. And we'd like to see if there's any surprising deviation or not what you expect. That's the thing we'd like to do here. Oops, I see just right now somebody mentioned I should read a comment. Sorry.
I think it's still a local experiment, but let's leave the discussion at this point because we have to go on. So okay. Thank you very much.
Yeah. Thanks. I just see there's a comment from Charles Robson who asked me why is the calculus not probing general relativity? The answer is the effect that you see could be explained by just Newtonian potential. Okay, so you could explain this without any space-time curvature, and that's the reason we say the cow is. But we just talked before, but has some limitation in the strength about concluding this GR effect, and therefore we would like to do something without masses where intrinsically there is no Newtonian potential.
Okay, so thank you very much, Philip. Excellent.
Thanks for the invitation. I'm very happy that I could talk here.
Good.
I have to get out for a second because my kids are screaming for homeschooling, so I'm running back to save some homework problems. Okay.
Thank you very much.
Thank you. Yeah. Bye.
These are usually the difficult ones.
Absolutely.
Okay. I turn over to you. Yeah, you're the chairman for the next
I guess so.
Herbert, may I suggest a 5 minutes break for everyone before we continue?
So shall we meet at 20 minutes past 11?
Very good.
That's
Can you hear me?
Yeah.
Will some of you be occasionally in this lunchroom where one can say hello?
In this lunchroom, actually, I have been before, but unfortunately, not really.
I mean,
I have tried it, and it looks a little bit like a computer game. So you can move around your little figure, and yeah. When I was in there was nobody else.
Okay.
Okay, almost.
Hi. Hi, we can hear you.
Okay, very good.
I've granted you the rights so that you should be able to share the screen. You're her co-host for this reason.
Okay, great. Let me just try.
Yes,
see if
you
it
can
works.
start and you don't have to start to talk immediately. Perfect.
So that should work, right?
Yeah, maybe you could make it full screen still.
Right. That's full screen, and then I can make this small such that you don't
Exactly. Perfect.
see the other people.
So, wir haben noch ein bisschen Zeit.
Ja, also vom Screensharing sollte glaube ich
Ja,
alles.
aufgezeichnet. Ich kann alles sehen und ich kann Sie auch perfekt hören.
Wunderbar.
Gut. Der Herr Mieling ist so nett und kümmert sich um die technischen Belange. Ich bin da sozusagen nur jetzt der Überbau, der ein bisschen...
moderieren, genau. Ich kümmere mich um die Berechtigungen, dass jeder, der Fragen stellen kann, das auch tun kann.
Perfekt. Das heißt, in der Question-Answer-Session kann ich dann ganz einfach, also in den Participants kann ich dann Raised Hands sehen.
Genau, ich werde die Leute, die die Hand heben, einfach...
Okay, ich würde dafür plädieren, das machen wir sozusagen am Ende.
Genau.
Gut, naja, wir sind schon fast.
Seht ihr eigentlich auch den Balken unten oder sehe den nur ich?
Ich sehe einen Balken. Ich habe meinen Balken drinnen, aber der verschwindet wieder.
Ah ja, okay. Ja.
Der wird von Zoom eingeblendet, aber der wird nicht beim Screensharing übertragen. Also wir sehen.
Okay, wunderbar, weil ich sehe den Balken, aber okay, ja. Dann.
Ja, das ist immer so, wenn man Bildschirm freigibt.
Okay.
Eine Möglichkeit auszublenden, aber wenn nicht allzu sehr stört, ist, glaube ich, einfacher so.
Ja, nein, also für mich ist das. Ja.
Übrigens, ich glaube, ich weiß, was der Piotr gemeint hat. Wenn man auf View Options geht, dann steht da Annotate.
Warum nicht? Aha.
War das gerade an mich gerichtet? Oder?
Nein, überhaupt nicht. An den Herrn Mieling, Entschuldigung.
Okay.
Das sehe ich gerade in der Funktion. Aber wenn das gut versteckt ist und wir haben jetzt...
Ja, genau. Security through Obscurity. Das ist das Beste, was wir tun können.
Ganz genau.
Gut. So, let's see. Okay, I'm not sure if everybody got his coffee and is already back. Yeah. Okay. So it's my pleasure to chair this morning session, so to say, after the plenary talk, and we will begin with Raffaela Wutte from the Technical University, actually my university, and she will tell us about the causal structure of warped flat spacetimes. And as I think you know from the abstract, it has to do with giving an explanation of, so to say, black hole entropy via state counting. Please.
Right. Yeah. Thank you very much for the introduction. Yes, it's my great pleasure to speak here. I mean, it's a great honor to get this opportunity. Thank you a lot. Thanks to the organizers. So I'm a PhD student at TU Wien, and today I'm going to talk about work that I did together with Stéphane Detournay, Wout Merbis, and Kim Seng. So our goal in this project was to reproduce the entropy of certain three-dimensional spacetimes, that warped flat spacetimes, through a microscopic derivation. And the plan of this talk will be as follows. I will start with a motivation and historic overview of how the entropy of the three-dimensional BTC black hole was reproduced using a conformal field theory derivation. Then I will discuss a new class of field theories, which are called warped conformal field theories. And then I will talk about the spacetimes that we studied, these warped flat spacetimes, as I said before. I will talk about the causal analysis, and then I will end with how their entropy can be reproduced using a warped conformal field theory. It's known since the 70s, after the seminal works of Hawking, Bekenstein, Bardeen, and Carter, that black holes behave like thermodynamic systems in the sense that they have a temperature and they have a very large entropy. And now, one question that one can pose is, can this entropy be derived through a microscopic derivation? And to answer this question, it's often useful to consider toy models. And one such toy model is 3D Einstein gravity. In 3D Einstein gravity, there are no gravitational waves, and the curvature is constant for all solutions of the Einstein's equations. In particular, the Riemann tensor looks like this for all solutions of the Einstein's equation. So locally, 3D Einstein gravity seems trivial. However, global properties allow for interesting solutions. And in particular, it was shown that for negative cosmological constant, black hole solutions exist in Einstein gravity. In 1992, Bagnados, Teitelbaum, and Zanelli found a two-parameter family of solutions that you see here. And here the two parameters are M and J, and L just comes in over the fact that this metric here solves Einstein's integration with negative cosmological constant, which is -1 over L squared. And for M greater than 0 and J being smaller or equal to M times L, this metric up here describes a black hole, which is very surprising because it has a constant curvature, and usually we're used to black holes having a curvature singularity. But this is, of course, not the case in 3D. Nevertheless, the solution describes a black hole, and the reason for this is because it has the defining feature of a black hole, namely a black hole region, as can be seen from inspection of this causal diagram. So the BTC black hole and ADS3 are locally the same as we said before, and in particular, the BTC black hole can be obtained as a quotient of ADS3. Braun and Hainaut studied in 1986 boundary conditions for asymptotically ADS3 spacetimes. And what they found is that there are infinitely many Killing vectors, leaving these boundary conditions invariant, and they have infinitely many associated charges whose Poisson brackets span 2 copies of the Virasoro algebra. And nowadays, this is often interpreted as a precursor of the ADS3 CFT2 correspondence, which conjectures that quantum gravity on ADS3 spacetimes is dual to a two-dimensional conformal field theory. And Andrew Strominger had a famous paper in 1997 where he used the analysis of Braun and Hainaut to show that the entropy of the BTC black hole precisely matches the Cardy formula. And the Cardy formula is a formula that can be intrinsically derived from a two-dimensional conformal field theory. And hence, in some sense, this gives some microscopic interpretation, so to speak, because you can reproduce the entropy of the BTC black hole through accounting, but it is accounting in a two-dimensional conformal field theory. And since then, of course, it has inspired a lot of work in this direction, and people have worked on asymptotic symmetries, and they have also worked on matching the entropy of certain spacetimes or certain black holes to an entropy on the field theory side. But most of these analyses are actually use the original analysis performed by Braun and Hainaut, and they usually involve ADS3 or the isometries of ADS3, SL2R plus SL2R. And in this talk, I want to provide an example of a matching for spacetimes which do not fall into this category. And work on asymptotic symmetries in general and in this direction has also led to the discovery of many new field theories. And one of these new field theories are so-called warp conformal field theories, whose symmetry algebra you see here. So they also have an infinite dimensional symmetry algebra, and they admit up to 3 distinct non-trivial central extensions, C, kappa, and K that you see here. And one nice way to understand warp conformal field theories is the following. Polchinski showed in 1987 that the symmetries of any 2D local unitary translation and scale invariant quantum field theory with a discrete spectrum of the datation operator enhance the 2 copies of the Virasoro algebra. And Andrew Strominger and Diego Hoffman considered something similar in 2011. They considered a quantum field theory with the same assumptions, but with scale invariance only in one direction. And what they found is that also in this case, you have symmetry enhancement. And in fact, there are 2 minimal options for the enhanced symmetry algebra that you get. You either get the symmetry algebra of a warp CFT or you get the symmetry algebra of a CFT. And you can get back to just getting 2 copies of the Virasoro algebra, which is the symmetry algebra of a CFT, by adding back the scaling in the second direction. But similarly, you can single out the warp CFT by adding a boost. Now, in our work, we were focused on certain 3-dimensional spacetimes, dubbed warp flat spacetimes. And here you see the metric of warp flat space. And the reason why it's called like this is because it's a vibration over 2-dimensional flat space. And this is a 3-dimensional spacetime, which is a solution to topologically massive gravity with positive cosmological constant. And here you see the equations of TMG. Lambda is the cosmological constant, mu is this coupling to the Cotton tensor. And this metric up here has constant positive scalar curvature, but it's not maximally symmetric. In particular, it has 4 killing vectors. And the algebra that they span is the centrally extended to the Poincaré algebra that you see here. So this would be the translations, T0 and T1, K would be the central extension, and J would be the boost. And it's kind of curious because we have positive cosmological constant, but the isometries that we have are span the algebra of 2D flat space plus a central extension. And now, so these spacetimes already appeared in literature, and Vikula 1 quotient appears, and it's the quotient along K, so it's a quotient along a shift, appears as the near horizon geometry of Kerr-de-Sitter black holes at fixed azimuthal angle in the limit where the outer, the inner, and the cosmological horizon coincide. But in our work, we were interested in a different quotient. In particular, we were interested in the following quotient, which is a quotient along a boost, a combination of a boost and a shift, and psi and omega are just 2 constants, which are introduced when performing this quotient. And these quotients were claimed to be black holes in the regime where psi plus 2 omega are greater than 0. And this is work that goes back to Musa and collaborators in 2008. And this was also originally the reason why we got interested in these spacetimes, because they were claimed to be black holes and they had this very funny isometries. And one of the questions that we tried to answer in this project was, are these warp flat quotients black holes? And to answer this question, we used projection diagrams, which were developed by Piotr, Christa Oels, and Sebastian Sipka in 2012. And these projection diagrams are useful to depict non-block diagonal metrics with 2D diagrams. And while they are similar to conformal Carter-Penrose diagrams, there is a crucial difference, namely that a projection diagram is not necessarily a slice of spacetime. Now let me give you the formal definition. This was given in the paper by Piotr Krusche and his collaborators. So let MG be some smooth spacetime, then a projection diagram is a pair pi u, where pi is a map from M to W. W is a subset of R11, and this map is continuous and it's differentiable in an open dense set. And U is a subset of M. This is an open set on which pi is a smooth submersion such that the following two conditions hold. That every smooth time-like curve sigma in pi of u is the projection of a smooth time-like curve gamma in u, and that the image of every smooth time-like curve gamma in u is a time-like curve in R11. So in particular, every time-like curve that you have in u gets mapped to a time-like curve in R11, and to each time-like curve in pi of u, there exists at least one time-like curve in u. And these conditions 1 and 2 ensure that causal relations on pi of u reflect as accurately as possible causal relations on u. Under the map pi, causal curves are mapped to causal curves, but for instance, many space-like or null curves become null or time-like. And another point is maybe that as it's possible to project in different ways, different projection diagrams may carry different information about the causal structure. So okay, let's get back to the question. So we wanted to answer this question whether the warp flat quotients are black holes. And so these are the projection diagrams, and the way that we obtained them was that we projected out the direction of identification, which is the most natural thing to do, I would say. And depending on the regime of the parameters that were introduced in performing this quotient, the spacetime either looks, the projection diagram of the spacetime either looks like the left picture or like the right picture. And the shaded regions in the right picture are the region that must be excluded from the diagram, because in this region, the vector along which we identify becomes time-like, which leads to the appearance of closed time-like curves. And the dashed lines denote the location of the Killing horizon that was claimed to be a black hole horizon in the paper I just cited before. And one can show that in both cases, the spacetime is not a black hole. And what we furthermore did in this paper was we have this Killing horizon, and we associate a Hawking temperature and entropy to it. And here the entropy is defined to be the Noether charge associated to the horizon Killing vector field. And in terms of mass and angular momentum, this entropy looks like this, where m is the mass and j is the angular momentum. And what we did for these spacetimes was we performed an asymptotic symmetry analysis and found that the asymptotic symmetries match the symmetries of a warped conformal field tree. And lastly, what we did was we showed that the gravitational entropy precisely fits the entropy that can be derived from a warped CFD. Well, thank you very much for your time and attention. And thanks to the organizers again.
Thank you very much for the nice and concise talk. You stayed perfectly in time. We still have some minutes for questions. So questions or comments, please.
May I have a question about this projection from upper space to this two-dimensional one? You said that the time-like curves are projected on time-like curves. What about cones, local cones? How did they project null cones in this general setup?
Maybe I can answer this?
Yes.
Yes. So of course, null cone is a limit of time. So null curves are limits of time-like curves. So if you have this control on the time-like ones, you get the causal ones by limits, by taking limits. So the only thing which probably in this definition might not work is that some null curves might come not come from null curves in space-time, right? So, I mean, in this definition, you could write a similar definition using causal, right? That nothing would prevent you to do it. But certainly the projection of null curves would be a null curve.
Ah, okay, thanks. No.
Rafaela, may I ask a question?
Sure.
Yeah.
So one can associate a temperature to a killing horizon, and but physically one thinks that this really should be associated with event horizons, right? And in this case, killing horizons are not event horizons. So how should one interpret this temperature now?
Of course, it's a very good comment. So of course, in the case of black holes, we precisely, I mean, we have this analogy, as you well know, I mean, to the laws of thermodynamics. I mean, that was found, and then what people have been doing is to extend somehow what we know from black holes also to cosmological horizons. The question of how well this really describes the thermodynamic entropy, I mean, it's not as clear as with black holes.
Maybe I can comment on this. If you think about, so to say, accelerated observers in flat space, there is also this Unruh temperature associated with this, and they also have, so to say, a killing horizon. It's so to say the killing horizon for the boost vector fields.
Right. That's true. Yeah.
Okay. So from your point of view, Herbert, the killing horizon would be actually the important thing.
Well, I mean, it works also in flat space. So you don't have a horizon in flat space, and you can have an accelerated observer that moves with respect to the Minkowski vacuum, but respect to a different vacuum, the Unruh vacuum. And one, with respect to the other, appears like a coherent state, if you want to. So in this sense, you can assign a temperature. It's not only a formal temperature in the sense that you read this like, let's say, the first law of thermodynamics, and then say, okay, one thing has to be the temperature, the other thing has to be the entropy. So there is sort of a physical interpretation.
Rafaela, do you think you could show your projection diagrams again?
Sure.
Yeah, so I think one of my problems when I see this is that, of course, normally when you want to do things, you want a globally hyperbolic spacetimes with Cauchy surfaces. And so the domain of auto communication in the spacetime, which if you just took the one quarter, take the right picture, take the right quarter of this picture, right?
Yeah,
this is not global. Now the right one, yes, the other one.
Ah, okay, sorry, this one, yeah.
My right, yeah. then this thing is not globally hyperbolic, right? Because of these causal curves which are there. So the projection diagram fails, but it's not that it has a gap, but this gap is real, right? So the gap comes from the fact that there are closed time-like curves in the spacetime. Right. So it's hard to do any reasonable field theory on this thing which has not globally hyperbolic, right? And that's why. As you just completely agree with you, this is not a black hole spacetime because it doesn't have good black hole properties, right?
But in some sense, I mean, so I mean, what I can say, I mean, is this is at least in 3D, it's quite standard because in what you actually have for the BTC black hole, I mean, you also do identification along the orbits of a killing vector, and what you also get in the case of the BTC black hole is you get a region where there are closed time-like curves.
But normally these regions are beyond the event horizons, right? So that's the point, right? So you have
right, but if I cut
here it's not, right?
But if I cut the space-time, yeah, right. But that's true.
If you cut this away, then you will get a boundary value problem rather than a normal, scry and stuff like that. And then all these notions of black hole just are completely different.
No, I mean this is for sure not a black hole. I mean,
right? Yeah, we agree with this, but I just wanted to point out that this is even more singular than not a black hole.
What I can say is, I mean, there are actually solutions whose causal diagram precisely looks like this. So these are referred to as flat space cosmologies. They are quite studied in 3D, and the way you obtain them is you get them as a limit from the BTC when you take the cosmological constant to 0. So in 3D, I mean, for 3D Einstein gravity, you only have black holes for negative cosmological constant, and it's shown that you cannot have black holes in 3D Einstein gravity for positive or null cosmological constant. But what people have been studying are these so-called flat space cosmologies, which would look precisely like this, namely you have this closed time-like curves, you cut the spacetime off, and what you end up with is the singularity somehow. Mm-hmm. I mean, the place where this closed time-like curves start to appear.
Thank you.
Okay. Further questions or comments? If not, then I would think we should continue on. And thank you very much. Let's thank the speaker again. Thank you very much for the nice presentation. And our second speaker in the morning session will be Leonardo Garcia Heveling from the University in Nijmegen. And I hope I have pronounced your name nearly correctly.
Yes, yes, thank you.
Okay. And he will tell us about causality theory of spacetimes with continuous Lorentzian matrix in a revisited form. Okay, please.
Thank you very much for the introduction and for hosting this event and having me as a speaker. Do you see the presentation now full screen?
Yes, perfect.
Okay, great. So, well, I don't have an outline slide, so I will just explain the title instead to give the outline. So the first thing I'm going to talk about is spacetimes with continuous metrics. What do I mean exactly, and what is the motivation for looking at that? Then I'm going to review causality theory briefly in the standard smooth case and also in the continuous case. And then in the end, revisit it. So I'm going to propose a new approach, and I'm going to explain what are the differences and what do we learn from that. So first, well, by a C0 spacetime, I will mean a C1 manifold with a C0 Lorentzian metric, so continuous metric, and a choice of time orientation. And then why do we care about this? So one motivation comes from the strong cosmic censorship conjecture, which in its modern form is essentially the question of whether certain smooth spacetimes can be embedded into a larger C0 spacetime. Another motivation are weak solutions to Einstein's equations. So if we want to model some phenomenon with the energy momentum tensor that is not smooth, is for example just continuous, then of course the solution will be also of a lower regularity. And lastly, more than a motivation to look at C0 spacetimes, just the kind of the approach I will take goes in the direction of axiomatizing causality theory, which is something that various authors have worked on for different reasons, just for mathematical reasons, but also this is motivated by quantum gravity, and also it is motivated by the desire to have a framework where C0 spacetimes, smooth spacetimes, different regularity classes can be understood. Okay, so first I briefly recall the causal relations on the spacetime. So the causal futures J plus are given by the pairs of points that are connected by a causal or non-space-like curve, and the chronological futures I plus, the same but for time-like curves. And then an important result in causality theory relating these two concepts is the push-up lemma, which tells you that if Q is in the causal future of P, then the chronological futures of Q and P are related by these two inclusions. So in the pictures, I show the future version. So this on the left would be the trivial case, and on the right would be the not so trivial case when P and Q are connected by a null curve. This is Minkowski, and the futures are included as here. And well, the curves I drew, they should motivate the name push-up lemma. Okay, but now what happens? So this lemma holds on smooth spacetimes. So what happens on continuous spacetimes? Well, it fails. This was shown by Fuchel and Grant in their 2012 paper. And the picture explains a bit why. So to understand this picture, it is easy. This can happen in any dimension, but in 2D it's easier to understand because in 2D, usually in the smooth case, the boundary of I plus can be found by just finding the two null geodesics, future directed, that start at P in the two possible directions. And you don't need to solve the geodesic equation. You just need the equation that the tangent vector is null. And now the initial value problem of null tangent vector starting, the curve starts at P and in this direction, for example, to the left. If the metric is smooth, it has a unique solution. But if the metric is only continuous, then it has solutions, but they're non-unique in general. And because of this, well, we have a whole family of null curves that start at P and go to the right, for example. And they span this whole blue region that will then be included in the causal future J, but not in the time-like future I. And this region in the paper it's called the causal bubble. And if we choose a point in the causal bubble, then obviously for the pair PQ, the push-up lemma fails because there is this red region which is in I plus of Q, but it's not in I plus of P, even though P and Q are causally related. Okay, and now, well, what could we do about it? So Sorkin and Woolgar already in 1996 proposed that maybe for continuous spacetimes, instead of having J plus, we should define a different notion of causal relation. And they made a proposal which is called K plus, but I'm not going to explain it because I'm going to make a different proposal, which sort of in analogy to theirs, I call it lowercase k instead of uppercase k. And it's defined like this. So 2 points being Q, I say that Q is in the K future of P if these two inclusions hold between the chronological futures. And now this has the consequence that the push-up lemma it holds by definition. That these two inclusions are precisely the statement of the push-up lemma, and now I have them, they hold by definition. And moreover, this K plus is the maximal relation with this property. So any relation that is bigger than little k plus will not satisfy the push-up lemma because by being bigger, it will include some pair of points where one of these inclusions fails. Okay, and now the first result, just a quick theorem, not very deep, is that this relation it is transitive, reflexive, and it is contained in the closure, topological closure of I plus. And well, this is kind of a reality check. Like we want these properties to hold to have something reasonable that we can call a causal relation. And now I will give some concrete examples to illustrate this. So in two-dimensional Minkowski space, we remove a point, and then we consider these 2 points PQ, which were joined by a null curve before, but now then this null geodesic is cut out because I removed the point in the middle. However, the chronological futures are unaffected, and there's still the relevant inclusions hold. Therefore, P and Q in this picture, they are K-related, even though they are not J-related, so not in the usual sense. And now, what happens if instead of removing a point, I remove a line? Then the situation is different because to the future, nothing has changed. But in the past, now the chronological paths of P and Q are disjoint because I removed this line. So now P and Q are not K-related because both inclusions would have to hold for them to be K-related. Nonetheless, Q is still in the closure of I plus of P. So we see here that the K relation is in general smaller than the closure. Okay. And now, well, this definition was just set theoretic. So can we still talk about causal curves is the next question. And the answer is yes. We can define them in the following way. So if you just look at this equation and the picture, what I'm saying is that for two consecutive points on the curve, what I'm asking is that the second one is included in the K future of the first point. Okay, and this has to hold for all pairs of consecutive points on the curve, which should be a continuous curve. And moreover, I want this to hold in a local sense. So that's why I'm talking here about neighborhoods, because otherwise I could have some kind of, let's say, interference of global effects. So for example, in some more pathological space-time, it could be that globally the K plus relation is everything, and then every curve is K plus causal, and I don't want that. So I consider it locally, and in particular, K plus sub U means K plus defined on the space-time U on this neighborhood, okay? And this definition, the same, but with its standard J, was already given, for example, in the classical book by Hawking and Ellis. And now we can use this to define another relation that I call K twiddle. So the twiddle kind of represents a little curve. That's the idea, because this relation is simply defined by taking those points which can be joined by a K plus causal curve. And here comes the next theorem. So on smooth spacetimes, this K twiddle coincides with the usual J. And this is important because this means that K plus twiddle is a valid generalization of the usual causal structure to the case of continuous spacetimes. Because in the usual case of smooth spacetimes, it coincides with the usual notion. And now, since we are talking about causal curves, we can wonder about the limit curve theorem, which is another important result in causality theory. So using the standard notion of causal curves, the one defined by the metric, the one that gives G, even when the metric is continuous, we still have a limit curve theorem. The fact that it still holds in the C0 setting was also shown in the same paper by Crucial and Grant. And this, well, let's say baby version of the limit curves theorem is the following statement. So we have a sequence of G causal curves, so causal curves in the usual sense defined by the metric. And this sequence uniformly converges against the limit curve gamma infinity. And the statement of the theorem is that gamma infinity is also a G causal curve. So the obvious question is, does the same hold for K plus causal curves? And unfortunately, the answer is no. At least, I mean, in the case of smooth spacetimes, yes, which is not surprising because I showed before that the relation coincides with J plus in the smooth case, but in the interesting case, which is continuous spacetimes, we don't have a limit curve theorem. And I'm going to give a rough idea why we don't have a limit curve theorem. And it's the following. So essentially, we have this limit curve, gamma infinity, and we want to consider a neighborhood. And then we consider two consecutive points on the limit curve. And we see them as limits of a pair of points on the sequence. Now, if the relation K plus is closed in the neighborhood, in the sense that this set here is a closed set, so the set of points in the product U times U which are related, then obviously gamma infinity is going to be a K plus causal curve because these 2 points lie in the closure of this set. And if K plus includes this closure, then everything is fine. But it turns out we have examples where this does not hold, the set is not closed. And in fact, we also have specific examples of sequences of curves which converge against a curve that is not causal. Even sequences of time-like curves that converge against a curve that is not K-causal. And this lets us draw a deeper conclusion, even because recall that K plus was the maximal relation such that the push-up lemma holds. So any relation bigger than K plus does not allow for a push-up lemma. However, we see here from this rough explanation that what we would need in order to have the limit curve theorem is to add more points. We would need to add the limit points. But if we do that, then we lose the push-up. So the conclusion is that both at the same time is not possible. And this, well, here I just gave a rough explanation, but in the paper, this point is made more precise. Yeah, and now I'm going to conclude the talk by briefly summarizing. So what have we done? The first thing we have done is we have developed a set theoretical way to construct the causal relation out of the chronological relation. And in particular, the manifold structure and the metric was only used implicitly in the definition of I plus, but other than that, we didn't use it. So in principle, if I give you a set and I give you a relation that I decide to call it the chronological relation, then one can construct the causal relation K plus out of that. So it's applicable in a very broad context. Furthermore, we have applied it specifically in the case of C0 spacetimes, and that has given us a causal structure that satisfies the push-up lemma, which is not the case with the standard causal structure. But we've paid the price of losing the limit curve theorems instead. So it was a trade-off. But as I just said, this is unavoidable. So what is shown in the paper is that if you take the I plus given in the usual way by causal curves, and the metric is only continuous, then there does not exist any relation playing the role of causal relation that would satisfy both the push-up lemma and the limit curve theorem. And furthermore, in fact, in the paper, it's also considered the case of keeping J plus given and then trying to find the suitable I plus. And also that doesn't work. Also then one has to sacrifice one important property. Okay, and this concludes my talk. So thank you very much for your attention. And here's the archive and identifier in case you're interested.
Okay, thank you very much for the interesting talk and also for staying perfectly in time. And I see we already have a question. So Claudio Baccanini.
So thanks for this very interesting talk.
Sorry, it's very low, so you have to maybe repeat the question.
Okay, so thanks for this very interesting talk. It's like this set theoretical definition is very interesting. It's something maybe that would be interesting to look at in the context of the causal fermion systems framework, because there you have sort of this problem where you have local causal relations, but there's no proper formulation of sort of like global causal structures yet. And yeah, it's a problem I've been thinking about before, and I think this work, what you've been doing here, might be applicable to that setting. So that's more sort of a comment.
Okay, thank you very much for that comment. I never thought about that, so I don't know much about causal fermion sets, but thank you. I hope it might work. Otherwise, the capital K plus of Sorkin and Wolgar might also be an option. Maybe you also want to check that.
Okay.
May I make a comment and a suggestion? So the first comment is that this last point on your slide is a very nice result. So I like this a lot. If you want to do causality theory, you need both the push-up lemma and the limit curve. And so that's the two tools that you have, and you can prove things with that. And if you're missing one, then you're just essentially, yeah, it's a, and you can do much less. So that's a very nice result. And second comment now, so one of the key things which one uses in causality theory is the notion of generators of horizons. And I've struggled quite a bit of trying to understand how to formulate this and get any result in this spirit. Maybe your K plus relation could be useful to define generators of horizons or something like that in for continuous metrics. So I don't know if you have thought about this, or if not, maybe that would be an interesting thing to do.
Okay, thanks for your comment. I have not thought about that either, but well, I'm very happy to see that there is a potential for application. And I agree with your previous point that really both the push-up and the limit curve theorem, and in fact also the openness of the chronological relation. I think those three are like the key tools. With those three, you can do all of causality theory basically, but if one fails, then it's pretty bad.
Okay, further questions or comments?
I would like to ask a simple question. Maybe the notion C0 space-time is misleading because it does not mean that the manifold is C0, yes? So this is just C0 with respect to the metric tensor, yeah? This is the idea. But what is the underlying structure of the manifold itself? Is it only differentiable or smooth or whatever? What kind of atlas we use on a manifold?
C infinity.
Yeah. Thank you. I use a C1 atlas. So in principle, the natural thing to do is to have the metric to be CK and then the atlas to be CK plus 1. Because,
only,
for example,
only. Mm-hmm.
Only, I mean, but however, there's a theorem that says that any C1 atlas has a C infinity sub-atlas.
Yeah, exactly.
So you could do that, but I think that if you choose a C infinity sub-atlas, you're making a choice that I don't want to make a choice, because maybe
it depends but it depends on the application. If you want to analyze the shells, for instance, it's easier to work with smooth atlas and distributions, you know, just.
Yes.
So it depends on the applications.
Otherwise, you don't have a concept of test function space. I mean, so.
Yeah, exactly. So.
Okay. Further questions or comments? Well, if not, then let's thank the speaker again. Thank you very much for the nice presentation. And we will move on to the last speaker of today's morning session, Lorenzo Gavazzino from the University in Warsaw. And the title of his talk is The Lyapunov Function of Relativistic Dissipative Hydrodynamics.
No, let me say he's not from university.
Okay,
No.
sorry about that. But I hope I got the city right.
From Warsaw, yes, but we have more centers, you know. Just.
So yeah,
it's not
I
from
apologize.
The
so it's from the
okay.
CAMKPEN in Warsaw.
Yes, because it was too long for staying in the space. But yes, the Nicolaus Copernicus Astronomical Center of the Polish Academy of Sciences in Warsaw.
Okay.
So,
please go ahead.
Thank you. Thank you very much. So good morning, everyone. I would like to thank the organizer for giving me the opportunity of giving this talk, although it's probably the topic is a bit different from what we have seen up to now. First of all, do you see the pointer also? Can you?
Yes.
Perfect. Okay. So we can start. So the topic of my presentation is relativistic viscous fluids. So first of all, in a nutshell, what is a viscous fluid? Basically, a viscous fluid is what you get when you remove the assumption that your little volume elements of the fluid are in local thermodynamic equilibrium. So in essence, equilibrium thermodynamics is no more enough to force and describe all the structure of the stress energy tensor, but you open the possibility for much more complicated structures. So suddenly you can have shear stresses, you can have flux of heat, even in the rest, flux of energy, even in the rest frame of the fluid, and this is what you call heat. And you don't even have anymore a clear notion of equation of state in principle. Everything becomes free. Now, while in Newtonian physics, everything is simple because basically there is general consensus on the idea that the best theory is Navier-Stokes. In relativistic hydrodynamics, it's more complicated. You have a whole landscape of many different alternative theories, and it's pretty hard to decide which one is the best. So in this talk, I will not focus on a specific theory. I will let this possibility free. But instead, I will say, let's imagine that we are a research group all together, and we want to create our personal theory for viscous fluids in relativity. So now the question is, what is the most important feature we need to guarantee if we want our theory to make physical sense in the end? Well, take the simplest example possible. Take a glass of water prepared like this, and you have put a vortex in the middle. So this is clearly what we say to be an out of equilibrium configuration. Here, all the complexity of hydrodynamics is evident. You will have probably shear stresses. It's basically an unexplored land. Everything is complicated. And so you will have a stress energy tensor with all these features. But if you wait long enough, after a while, you will get a configuration that's somehow like this. Now, this state can be described using conventional statistical example of equilibrium statistical mechanics. And if you do all the calculations, you will immediately discover that, for example, it's necessary to have a isotropic stress, and that this stress coincides with the thermodynamic pressure. So in the equilibrium states, all this complex structure needs to reduce to the perfect fluid structure. A viscous fluid is indistinguishable from a perfect fluid in an equilibrium state. So this is the first feature you need to guarantee. But there is actually more. Because as I said, if you prepare the glass of water with the vortex, after a while you go here. But the reversed process must not happen. If you start in equilibrium, you don't see vortices spontaneously pop up inside your glass of water. So somehow you need to guarantee that while this process is allowed, this other one is not. If you put this statement in mathematical terms, this is a stability requirement. You want the equilibrium state to be stable against perturbation, or any perturbation, you want it to decay and not to grow. Now, it turns out that while in Newtonian physics, this is quite easy to guarantee. In Newtonian physics, you just, you make all the calculations with Navier-Stokes and you get positive specific heat, speed of some square positive viscosity coefficient, everything is well understood. But if you move to relativity, everything is more complicated. If you take the straightforward generalization of Navier-Stokes to relativity, basically what you obtain if you just promote J to nu everywhere, then you get the theories of Eckart and Landau-Lifshitz, and you discover that they are unstable. If instead you add more elements here and there, and you create something like Israel Stewart, and you try to make the theory hyperbolic and so on, then you manage to make it stable, but the meaning of the stability conditions that you get is really hard to understand. You have in front of them, they look completely mathematical, and you don't get what is happening. So answering what is happening here was the main goal of our research. This is what we studied. And we started with the simplest question possible, a very physical question. And the question is, why don't we see vortices spontaneously pop up in a glass of water? Why don't we see it in nature? Well, if you open a good book of thermodynamics, you find the answer. And the answer is quite simple. So basically, the idea is that you have a function that you call entropy. Then you define the equilibrium state, the thermodynamic equilibrium, as the maximum of this function. You assume that it always exists. Now, if you don't have broken symmetries or these complicated things, but you assume to work with a simple fluid, you can also guarantee that the absolute maximum is achieved only here. So you have only one point in which the entropy is maximum. And then you have the second law that tells you that the entropy can only increase, it cannot decrease. So if you combine all these three statements, you realize that these are just the hypothesis of Lyapunov stability theorem. And so you can conclude that the entropy is Lyapunov function of the system, and that the thermodynamic equilibrium state must be Lyapunov stable. Lyapunov stable just means that you start close enough to the maximum, you stay close enough to the maximum. And the intuitive explanation is clear. If you want to move away from the thermodynamic equilibrium, you need to reduce the entropy, but this cannot happen. And this is just the mathematical reformulation of the Gibbs stability criterion. So the question is, what happens in relativistic hydrodynamics? So first of all, how do we define the entropy? The entropy is defined typically through an entropy current. The entropy is constructed as the associated charge to this current. And then the second law of thermodynamics is imposed in a divergence form in this way. Now, apart from one theory that I will not discuss here, this condition is always ensured as an exact condition, and this is fundamental. If you really want the Lyapunov stability theorem to apply, you need this condition to be exact. And then if you assume your space-time to be sufficiently simple, you have a finite system and you take two hypersurfaces, one in the future of the other, you can use Gauss' theorem, and you will get that from this follows that the entropy grows. So our theories, all the theories that we are going to analyze, satisfy this condition. Therefore, if we have instability, something here must be broken. So what we just did was to take all the most important theories around, study the structure of the entropy, and see what happens. And indeed, what we discovered is that what actually is broken is the condition that the equilibrium is the maximum of the entropy. And here we come to the most important slide of the talk. If you want to remember something, I ask you to remember this. So the idea is the following. Here you have all the unstable theories. Here you have the stable theories. This is a plot of the entropy. The green dot here is what you assume to be the equilibrium state. Now, the blue line here are those states that have a Newtonian analog. So those states that you are able to take the Navier-Stokes equation, solve them, and you get solution that you can see in parallel to this. While you see there is a new axis, and so a bunch of new states. All these states are states that are strictly impossible in Newtonian physics. There's something completely new that was not conceivable if you use just Navier-Stokes. And what you discover is that in these new states, the unstable theories have the property that the entropy grows along these states. So if you move slightly out of equilibrium, since the entropy can only grow, the system will escape in this direction. And so in the end, basically, I just want to give you an intuition of what these states are, just to understand what is happening. So you take water, take the ocean. Imagine that some heat goes to the left. Now, in relativity, you know that energy flux is equal to momentum density, and therefore you know that if you want the total momentum to be conserved, the fluid must accelerate in the opposite direction to conserve the total momentum. But if you do all the calculation, you discover that in the stable theories, the entropy grows in this configuration. So the system cannot go back to the initial state in which it was at rest, because this would reduce the entropy. Instead, the entropy will keep growing. And so the speed keeps increasing. The fluid starts rocketing, using heat as a rocket fuel in the opposite direction. And this is what drives the instability. So this kind of stuff is not possible in Newtonian physics, as you can see, because it's something that happens only because momentum and because heat carries momentum. So with this, I can conclude. And the main message of the presentation is that be careful when you build your entropy, because thermodynamics always wins. Thank you.
Thank you very much for this concise talk. And since we are now back on schedule, actually, we have time for some questions. So please. Okay, any comments? So maybe
I can ask a question from a partial differential equations perspective. So yes. If you want to solve partial differential equation, it's good to have energy because it controls the solution as it evolves. And then if you study some systems, there's this notion of entropy solutions where you have many solutions. The entropy allows you to pick up the best one. So if you take theories of the kind you're doing here, would any of this still apply? Have you ever thought about how this could fit with PDEs and
yes. Okay. So first of all, the idea of energy here, you have even more, because you have energy and momentum. You have all the constants of motion of the system, and all this state space that I'm showing here in this picture. We are already restricting our attention to state with given energy and momentum. So you take all the possible configuration of the fluid, you restrict our attention to those that are dynamically accessible. So you are at fixed energy, fixed momentum, fixed particle number. You fix all the possible constants of motion that you have, and then you solve everything in this space. So these are plots in this context. Of course, if you let the energy be free also to change, then everything becomes different. But all these arguments are now you can also see the parallel in PDEs. For example, I can give you an element. If you take, for example, the equation of the bulk viscosity. Bulk viscosity tells you that the bulk stress is proportional to the divergence of the velocity. Now, if you move to relativity, the divergence of the velocity becomes the forward divergence, and you get a time derivative. But then when you go to the, when you put it in the divergence of the stress energy tensor, then you get another derivative. So the Navier-Stokes equations are of the first order in time, but naturally when you move to relativity, you get second order in time. And this is what creates this new axis, actually, from the point of view of PDEs. So all these new states exist because you go up of one order in the partial differential equations due to the fact that you have symmetry between time and space. So Navier-Stokes is first order in time, second order in space, but then you mix them and you get second order also in time. And this is what creates new axes. So you can also look at it from the point of view of partial differential equations, and you can also read all this problem of stability in terms of well-posedness, although we didn't go in this direction. There are some papers that before were analyzing it in terms of well-posedness of your initial value problem.
Thank you.
Okay. Further comments or questions?
Yep.
Okay.
All these viscous fluid theories, they have a problem with relativity to begin with, right? I mean, as far as I'm aware, all of them have sort of a length scale built in, and so there's this whole question of domain of validity of these theories to begin with, because obviously, if one observer formulates the theory, a strongly boosted observer would not agree that certain length scales are small and that the theory is valid to begin with.
I understand, yes.
How does this consideration on thermodynamics play into this sort of domain of validity of the theories sort of considerations?
Well, actually, this is an interesting question. So typically, when one works making hydrodynamics model, they have in their mind the reference of the kinetic theory. And kinetic theory might have, in principle, these issues too, right? Because when you define your distribution function for the particles, it's actually something that you define in the point. But you don't have big issues. I mean, I understand that there is this problem of length scales, but I don't. If you ask me like this, I'm not able to imagine how this should reflect in the mathematics of this problem. So I'm not sure of what you have in mind.
I mean, as far as I understand it, that's also, I mean, that's part of the issue why there are so many different formulations also of relativistic viscous fluid theory. Because sort of how to take account of this sort of minimal length scales is, there's a non-unique way how to do this, as far as I understand.
No, actually, the problem is that you want to have hydrodynamics emerge when you take kinetic theory and somehow you reduce your degrees of freedom, because kinetic theory has all the degrees of freedom of a function that lives in a 7-dimensional space, while you want to have hydrodynamics, which you just want to be a field theory, basically. And, once you assume that you are already at the level of kinetic theory, this problem of length scales has already been removed. Okay. So the problem is to move from kinetic theory to hydrodynamics. But once you are already a kinetic theory, somehow you can already forget about the problem of the length scale.
Okay,
I'm not sure if...
understand it, but yeah, I don't fully understand that, but I guess I'll take that as an answer.
Okay, in real life, I would say, okay, maybe the two gentlemen could discuss this in private. In principle, you could do this, I mean, on a private channel. Thank you. So if there are no further questions or comments, I would like to thank all the speakers of this morning session. Thank you for your participation and your contribution. And I would like also to thank all the participants for attending and asking questions. And in particular, I would like to thank Thomas Mieling for being such a great technical operator and making all these possibilities working so smoothly. And yeah, finally, I have to say we are now off for the lunch break, and we will reconvene at 2 o'clock. So thank you very much.
Thanks for the kind words.
Bitte, bitte. Das Mindeste.
Piotr, I make you host again.
Ich höre dich und ich habe schon das, ich werde das Livestream